keeps talking about 0 to 60, towing numbers, and giant touchscreens. Almost nobody talks about the one part that actually makes or breaks the Silverado, the battery pack. Because if you get the battery wrong in a full-size electric truck, you don't just lose a bit of range, you end up with a slow, heavy, overheating brick that dies early and charges like a 2012 phone. So in this video, we are going to strip away the marketing and walk through the Silverado EV battery like an engineer. What chemistry it uses, how pack is laid out, how it handles towing, fast charging, and what the BMS is really doing when it silently cuts your power on a hot day. By the end, you'll know enough to look at any truck spec sheet and instantly see if the battery system makes sense or if it is lying to your face. What GM is actually trying to do with this pack? Let's start with the big picture. The Silverado EV is built on GM's Ultium platform. That means this pack wasn't designed as a one-off science project just for this truck. It was part of a Lego system that also has to work on their SUVs and the Hummer EV with different capacities and different motor layouts. So when GM designed the Silverado EV battery, they had a brutal checklist in front of them. It has to store a massive amount of energy, somewhere in the ballpark of around 200 kilowatt hours in big configurations. It has to deliver serious power for towing, highway mergers, and launches from stop. It has to fit between the frame rails without destroying ground clearance or cab packaging. It has to survive abuse from owners who will fast charge, tow uphill, sit at full charge in the sun, and ignore every reduced speed suggestion. And it has to be buildable in volume with shared parts across multiple vehicles. If we keep that in mind, the tech choices GM made start to look less random and more like forced moves. At the core of this battery, you don't have cylindrical cells like Tesla. You have large pouch cells. GM's Ultium cells are big flat pouches with a nickel-rich lithium-ion chemistry. Usually a blend sometimes referred to as NCMA, nickel, cobalt, manganese, aluminum. The idea is simple. High energy density, reduced cobalt content, and chemistry tuned to handle the demands of big pack and of big power. A pouch cell is like a soft pack of cards. Inside you have a stacked layers of coated foil, anode, separator, cathode, all soaked in electrolyte. When the truck discharges, lithium ions move from one side to the other. Electrons go through your inverters, motors, and the whole thing behaves like a gigantic aggressive power pack. Why pouches instead of cylinders? Because pouches let GM change the cell size more easily and stack them into modules with a very high packing density. You don't waste as much space on metal cans and gaps between them. You can stack them side by side like books on a shelf instead of cans in a box. But there's a downside here. Pouch cells are mechanically floppy. They need careful compression and support so they don't swell, split, or lose performance. That is why Silverado EV pack is as much a structural and thermal design as if it is an electrical design. From cells to modules to the Silverado pack, those individual Ultium cells don't go straight into the floor as raw pouches. They are grouped into modules. Think of a module as a mini battery pack, fixed the number of cells fired in a series and parallel, clamped and compressed with its own sense connection. Multiple modules then get bolted and welded into the full pack, which stretches underneath the truck between the axles. In the Silverado EV, you are dealing with a very large pack footprint, because GM is chasing long range and heavy duty use, not a small city car duty cycle. To reach the total energy, GM stacks enough modules to get both the right voltage and the right kilowatt hours. Voltage is set by how many cells are in series in the stack. Energy is set by how many cells in total you have. More cells in series raises pack voltages. More cells in parallel and more modules raises total energy. The Silverado pack runs at what we would call a high voltage system, roughly in the typical EV range of 300 to 400 volts nominal. But GM does something clever on the Ultium platform. Like the Hummer EV, the pack can be logically reconfigured for fast charging. Inside, the pack is essentially built for two large halves. that can be wired in series for high voltage DC charging or in parallel for the normal driving configuration. This lets the truck talk to higher voltage fast chargers without needing a separate giant DC-DC converter. It is a smart way to make a big pack charge faster using existing DC infrastructure. So structurally, what does that look like? You have a flat pack, broken into the large blocks internally, with pouches stacked and compressed into modules. These modules are mounted to cooling plates, connected by bus bars to carry the high currents, and all wrapped in a sealed enclosure that doubles as part of the truck's underbody. The BMS, voltage tap boards, temperature sensors, and contactors live inside this enclosure. When you're looking at the battery, you're not seeing just a container. You're seeing an integrated mechanical, thermal, and electrical system that had to be packaged within millimeters to clear suspension, drive units, and crash structure, voltage, current, and what it takes to move a truck. Now let's talk about power, because this is where the truck owners start to care. To move a heavy Silverado EV plus payload plus trailer, you need a huge power packs, but you also need endurance. Power is a voltage times current. You can either crank up the current or you can run higher voltage. Higher current means thicker cables, more heat, more losses. Higher voltage lets you get the same power at lower current, which keeps cabling and bus bars reasonable. GM's Ultium strategy is to operate in that high voltage sweet spot. The pack voltage feeds 1 or 2 drive units, depending on configuration. Those drive units contain inverters that convert the DC battery voltage into AC waveforms for the motors. At full throttle, the inverters and motors might be pulling hundreds of kilowatts from pack for short bursts. This is where thermal design and cell chemistry meets reality. If the internal resistance of the cells is too high, every time you launch hard or tow uphill, the cells turn more of that current into heat. Heat is lost range, but more importantly, heat is aging. A pack that frequently overheats during heavy load will degrade faster. So GM's battery engineers had to balance 3 things. Energy density, so the pack can store enough energy without becoming ridiculously huge. Power capability, so the pack can deliver large bursts without sagging or overheating. And cycle life, so the pack doesn't die after a few years of towing and fast charging. You cannot maximize all 3. You choose a point on a triangle, and then everything from cooling plate design to BMS software is tuned around that choice. Cooling, the quiet hero, especially for towing. Cooling is one of the make or break parts of an electric truck. On a normal EV sedan, you worry about repeated fast charges and spirited driving. On a Silverado EV, you have to assume some owners are going to hitch a big trailer, drive up long grades at high ambient temperatures, and then plug into a fast charger at the top. That is worst case battery stress. The Silverado EV pack uses liquid cooling. Coolant channels run under or alongside the cell's stacks, pulling heat out of the modules and sending it through heat exchangers. The cooling system is tied into the vehicle thermal loop, which may also handle cabin HVAC and power electronics cooling. When you tow, current demand goes up and stays up longer. The cells heat more. The BMS is watching cell temperatures and pack temperatures constantly. If the pack gets too hot, it will start reducing power. That might show up to you as a truck feeling lazy on a climb or giving you warnings about limited performance. The same things happen on fast charge. Big pack, high state of charge, and high ambient temperatures is where you hit the limits fastest. The BMS will cut charging current to avoid crossing cell temperature limits or cell voltage limits. On paper, the truck might support very high fast charging. In real life, you will only see those numbers in a really narrow window. Moderate state of charge, cell temperatures in the sweet spot, and a charger that can deliver the power. So a key question for the Silverado EV isn't just how big is the battery, but how aggressively does the thermal system manage that battery? Long term, this is what separates a truck that keeps most of its range after years of towing from a truck that feels tired after 2 or 3 summers. Under all of this hardware is the thing we talk about a lot in this channel, the BMS. In a truck like the Silverado EV, the BMS is not a side piece, it's a central nervous system. It estimates state of charge across a large pack, where different modules may age differently and cells may not be identical. It estimates state of health, tracking how the capacity and internal resistance of the pack changes over time. It sets power limits for the both charge and discharging based on temperature, voltage, and health. It manages contactors and pre-charge circuits so the high voltage systems can safely connect and disconnect from the rest of the truck. It also coordinates cell balancing so that no one of cells or group of cells drifts out of line and starts limiting. When your Silverado EV tells you it has a certain predicted range, that is the BMS doing the math in background based on pack history, recent driving, temperature, and capacity. When your truck slows fast charging at high state of charge or cold temperatures, that is the BMS protecting the cells from lithium plating or overvoltage. When you see reduced power warnings, that is the BMS refusing to let the pack cook itself under repeated hard pulls. In other words, the Silverado EV battery pack isn't just a physical Ultium pack. It is a combination of chemistry, mechanical packaging, cooling hardware, and BMS software. Change any one of those, and the actual user experience on towing days and road trips change completely. Let's be honest about the challenges here, because they are not small. First, weight. A big pack means heavy truck. That hurts efficiency, increases brake and tire wear, and can reduce payload if you're not careful with the chassis design. GM has to use the pack as a structural element to claw back some of that penalty, which means the pack case, cross members, and mounting points are doubling double duty as part of the frame or unibody structure. Second is cost. Battery cells are still the most expensive single component in an EV. Doubling the pack size compared to a sedan doesn't just double your range, it doubles your cell cost exposure. So the question becomes, how much energy do you really need to make this truck usable for commuting, towing, and road trips without pricing it out of reach? Third is charging. It is easier to dump 60 kWh into a mid-size EV than to dump 150 plus kWh into a truck on the same charger. You can improve peak charge rates with pack reconfiguration and good cooling, but physics still wins. Big packs simply take longer to fill, especially if you want them to last more than a year. Fourth, duty cycle. A truck owner who tows regularly, hits fast chargers often, and lives in a hot climate will stress the pack much harder than a commuter in a crossover EV. GM has to calibrate the BMS to handle worst-case users, not ideal ones. That means conservative charge curves, power limits at high temperatures, and safety buffers at the top and the bottom of state of charge. All of that is necessary to avoid early pack death and warranty disasters, but it also means the headline numbers you see in presentations are the best case, not the everyday case. So here's the real question. Does the Silverado EV battery tech make sense for a truck, or is it just an SUV pack shoved into a pickup shape? From an engineering point of view, the Ultium approach is logical. Large energy content to cover trucks, aero drag, and mass. Modular pouch. Large energy content to cover truck aero drag and mass. Modular pouch-based architecture to share parts with other vehicles, liquid cooling, and clever pack configuration to hit high DC fast charge rates with existing infrastructure. All of those are rational choices. Where this battery lives or dies in the real world will come down to calibration and thermal control. If GM is aggressive on power and charging to chase headline numbers, the pack will feel impressive in the short term, but may degrade faster under heavy use. If GM is conservative, the truck might feel slower to charge compared to what people expect from brochure, but the pack will last longer in the hands of a real truck user. There's no free magic here. For a truck this big and this capable, energy has to come from somewhere. You either carry more of it in a bigger pack or you limit what customers can do with the truck. GM is clearly choosing the big pack route and building the battery as a core structural and thermal element of the whole vehicle. If you look past the marketing, that is really what Silverado EV battery tech means. They're trying to make a battery that is not just a fuel tank replacement, but a platform, something that can deal with towing, fast charging, and daily abuse without turning into a giant, expensive cumbersome. Whether they hit that target will show up or not in launch reviews, but in what owners report after 5 years of real use. So now, when you see someone say, the Silverado EV has a big Ultium pack, you should not picture a single giant block of energy. You should see thousands of pouch cells stacked into modules, bolted into a pack that is carrying a truck cooled by liquid loops and monitored by a BMS that is constantly juggling power, temperature, safety, and degradation. The truck you feel on the road is not just motors and torque. It is some of those choices. Cell chemistry, module layouts, pack voltage, cooling design, and conservatives or aggressive BMS limits. If you want to go deeper into how the BMS inside pack estimates state of charge and state of health, click on the link in the description. Thank you.